Hi, everybody. It's Tyler here at the University of North Dakota SIG event at Mall of America, checking with 32992B COGNEX, who's been having a great performance so far. One of the best backpacks that we've seen so far as well, too. Just overall great design. We'll be talking about some more of that design, what they've been going through for things. And if you take a look at this robot, just overall very well built, and their packaging looks great, too. They also have some cool custom software we'll be diving more into and how they're utilizing that and getting the feedback for that as well. And so a lot of great things for you to pay attention to. Let's learn more about them coming up here on Bits and Parts. Dylan, let's start the breakdown of this robot here. First off, we were talking earlier, this is kind of like iteration 2 for you, right? So I'd love to hear just overall some of the build design to it, and then some specific mechanisms we can break down into this too would be great.
Absolutely. So what I want to start with is talking about the packaging on our drivetrain. As you can see, a lot of the structure on our robot is towards the front. So something that we did is we counterbalanced that with our brain, our battery here, and also the tank is difficult to see, but it's also very towards the back and very far down on our robot, which gives us pretty good center of gravity. Even though this robot kind of tips as we're going through match play, it never really fully falls over because the center of gravity is so low.
Do you have any plans to improve your center of gravity at all, maybe for future events?
Yeah, so there is still a lot of structure towards here at the front. We could do some weight savings near the hood, near this area where we have our hood, our other hood here. The structure is kind of a little heavier than it necessarily needs to be. The aligner as well. This high strength shaft is a little high, so there's definitely some ways we could improve that. But having the tank, the battery, and the brain so far down low to the robot is definitely really helping.
Let's break down some of the other mechanisms in this robot. What do you want to start with?
Yeah, absolutely. I'll start with the backpack, which has been the thing that we've tuned the most on this robot overall. So one important thing that we have here is we run flex wheels at the bottom, and that really helps with agitating the balls that are in the backpack. And that helps, like, there's many kinds of jams that you can have where the balls fall in different orientations, and you're getting balls that aren't touching the wheels or are touching the wheels but aren't funneling correctly. But those flex wheels at the back really get a lot of grip on the balls and are able to funnel them, as well as making sure that we don't get jams where balls aren't touching our main rubber band roller. Additionally, we have some things on the sides here. We have the mesh on this side can contact the channel for our motor mount, but on this side we use 2 screws here that ensure that balls don't get in a very specific position where they can get up behind this sprocket, and then that causes interesting jams where the balls will kind of go around that and then not touch our flex wheels or our band roller. So a big part of tuning this has been making sure that there's no spots where balls can get, where it's kind of like a dead zone. That kind of takes me into our intake, where one interesting thing we have here is between our snail and our backpack rubber band roller, we have this band here, which completely eliminates an interesting dead zone we get there, where we can't have the ramp follow all the way up into the backpack. So we need that rubber band there to maintain contact with the intake. Then you can see we've got some standoffs here and around, helping with that funneling. Another issue we had a lot is one ball slowing down slightly in the snail, and then another ball coming up behind it at an angle and pushing it even further to the side. So these funnels really help solve that problem.
Overall, very robustly built and performing great so far. Lucas, let's talk about some of the driver controls on this robot too. I'd love to see just kind of the journey and the pathway that this takes, but we were talking earlier, you got a lot of different macros on your bot that you're utilizing, so talk to me more about that. And then I'd like to hear maybe a little bit more about just some drive strategy during matches, what you've learned so far.
Yeah, of course. So our drive controls are really simple but insanely useful. Each of our back plans have exactly one purpose, and each of our scoring stages is one button. So our top left is intake only to our backpack, and our bottom left would be outtake for the low goal. Our top right would be top goal, and our bottom right would be the center goal. So yeah, you can see. And with the controls, the piston automatically moves for me to score either in the backpack or out into the goals. Besides that, we utilize these scuffs, so I can keep my fingers moving on the joysticks at all time. And so my bottom left scuff activates the match loader, so it keeps me able to drive in it at a fast pace. But we utilize a switch key, which is probably what I think is most helpful from this all. Using the switch key and using this back left button, we go to a prime state. So since we have a backpack, we don't have a snail, and snails are obviously a lot faster in scoring than backpack, because snail automatically goes to the top of the intake and it's straight to scoring inside the goal. So using this prime state, just by clicking this, all the blocks get float up all the way to the top, which allows us, while we're driving to the goal, once I hit this prime state, all the balls are ready for me to score into the goal at a fast pace. And one quick little thing is, we have a fail safe just in case something goes wrong with a robot. In any scenario where either a ball can get stuck after match loading right here, or it just gets jammed inside the robot, pressing X by itself, it turns all the motors in a way where no matter what spot it's in, it's getting unjammed. And that's been really helpful in matches. It's been proven recently, because usually you would have to spin around, you have to press a bunch of buttons to get unjammed, but with just pressing the next, it's a quick and easy fix, which allows me to get back into scoring.
You've had a few matches under your belt so far here at Mall. What are some of the key things maybe you've learned from your competition so far that you might take into either eliminations tomorrow or future events?
Yeah, of course. So something really important I've seen is a lot of people aren't playing middle goal. The middle goals, just with one ball in them by itself, you already get the bonus points, which has proven to turn a lot of matches for us. So in the beginning of a round, we will usually be trying to fill up a long goal immediately with all our balls, and we'll play defense upon the other teammate and just protecting our goal. But at the last second, we'll leave, which gives them time to think, oh, I can go score in this long goal. But we'll get control of both middle's goals, which gives us a complete turn in the points.
Well, we wish you best of luck on that aspect for sure as we go into the next day at Mall. But we got to talk more about some of the code aspects of this. Let's pass it over to Thomas to talk about that. You're doing some cool stuff with localization, getting feedback as well, too. I know we're going to be showing a few things on screen, so what do you want to break down?
So I'll first finish off the robot here. So as Lucas was talking, we have a fail-safe in which if it's jammed, it will recover. But to avoid that state, we have a lot of casework where we basically detect if it's jamming. So from the motors, we can get the velocity, we can get the torque, and we can get the voltage. And so in certain conditions, we can see if, for example, it's jammed right here, and then spin back all of the intake such that it unjams it. And that has helped a lot, especially for auto and for driver, where you can't really control all the motors yourself and be able to unjam it. So that has definitely been a big part in tuning. That's taken a lot of work because there's so many edge cases and so many places it has jammed. I definitely think that's one of the reasons this robot has been really solid. So yeah, that is the programming aspect for the build. Another thing that we decided to do for this robot is that a big part of autonomous routines is knowing where the robot is, because to go somewhere you have to know where you are to be able to go there, right? So a lot of teams have used odometry. A lot of teams have used odometry for the past few years, and that has a lot of benefits. It's very consistent. It's sort of easy to build, but since it's only based off relative positioning, it can be inaccurate and it can build error over time. So to combat that, we have a set of distance sensors on every side of the robot, and do something called, we implemented an algorithm called Monte Carlo localization. So what this algorithm does is it effectively simulates a bunch of positions where the robot could be, and then it compares the expected distance to what the distance sensors actually measure. And so based off of that, we effectively determine where in all of the positions in the field it probably is. And so that gives us a very accurate position of the robot based off of only the distance sensors, so we don't build error over time. Now this approach does have a problem, and it is that it is very noisy and it can be inaccurate sometimes because it's inherently random. And so to prevent that randomness, you want accuracy and consistency in autonomous routines. What we do is we combine odometry and MCL into one accurate and smooth guess. And so for that, we decided to use an alpha beta filter. So effectively, we use the odometry to move the guess of the robot, but we use the Monte Carlo localization to provide measurements on the actual position of the robot. And so over time, it is able to sort of shift the prediction of the robot while keeping the smoothness of the odometry. And that has probably worked the best out of the few years we've did odometry. It's definitely worked better. Also, for testing all this, it is very hard to conceptualize particles and positions and all that based off of just what the robot does. So we developed a tool called the visualizer, or what we call the visualizer. Effectively, it allows us to visualize the particles of the robot, the positions it thinks it is, and so we can compare where it is and where it thinks it is, and then kind of tune and sort of troubleshoot the various algorithms we use.
Overall, an extremely complete package you've had so far, and it's very early in the season, obviously, and pushed back, right? So we can't wait to see what your team continues to come up with. But of course, wish you best of luck here at the Mall of America event. Can't wait to see feature designs, and best of luck the rest of the way. Thanks a lot for taking time to tell us more about it.